So the coefficient matrix for this problem, so the coefficient matrix is given and it's equal to minus 1, A, 1, minus 1. So the characteristic equation associated to this matrix is lambda squared minus the trace. Again, the trace is you add the element of the diagonal, you add them up. So this is equal to minus 1 plus minus 1, that's negative 2 lambda, plus the determinant. So minus 1 times minus 1, that's plus 1, minus a times 1, a equal 0. So this gives me lambda squared plus 2 lambda plus 1 minus a equal 0. So now we need to solve this equation. There are many ways we can solve this equation, okay? Either quadratic formulas, etc., etc. But here, it's really nice to see, and so that's why sometimes it just takes a little bit of time to look at your problem, and you will be able to somehow see some nice stuff. So here, for example, this is just lambda plus 1 squared minus a equals 0. And if I want to solve it, I will get lambda plus 1 squared equals a. So you see here, lambda is equal to minus 1 plus minus square root of a. So this is, of course, just plain algebra. But you can also, for example, use quadratic formulas another way. Okay? And we get lambda equal minus 2 plus minus square root of 2 squared 4 minus 4 times 1 minus a over 2. Okay, so being careful, this will give us lambda equal minus 2 plus minus square root. Typical mistake, if you forgot to put these two parentheses here, okay, some students will put minus 4 minus a, and that's not the case. Putting the parentheses helps me avoid that mistake, and they will get 4 minus 4 plus 4a over 2, which leads to minus 2 plus minus square root 4a over 2. Square root of 4a, that's 2 minus 2 plus minus 2 square root of a over 2, which leads to the same root that we found above, which is minus 1, minus 2 over 2, plus minus, we cancel the other 2, square root of a. So you see, if a is equal to 0, if a is negative, you have imaginary number. If a is, so here, if a is negative, we have complex lambdas, okay? If a is positive, we have two different lambdas. And finally, if a is equal to 0, we have one double lambda equal minus 1. So the eigenvalue is minus 1 for a is equal to 0. So the answer to the problem is a equal 0. For what value of a the system has a double eigenvalue, the answer is a equals 0. So for that a equals 0 now, we want to solve it. We have lambda. So we found the eigenvalues, minus 1. So first, we look for the eigenvector. So next, we look for the eigenvector. So it will give us one straight line. So we get here minus 1 minus lambda, okay? And it happens that minus the a of the matrix coefficient and the lambda are the same. So we get minus 1 plus 1 times x1, of course I'm taking the eigenvector to be x1, y1. And then you have plus 1 times y1 equals 0. And the second one is going to be 0 times x1 plus minus 1 plus 1 times y1 equals 0, which reduces to the equation minus 0 times x1, so y1 equal 0. So your vector is x1, 0, and since it's equal to x1 times 1, 0, we will take 1, 0. So y1 now, we found y1. y1 is e minus t times 1, 0. That is the straight line solution that we have associated to this system. And there's only one because we have a double eigenvalue. Next, we look for y2. So here, the second solution, linearly independent from y1. So we look for y2. We know that y2 is equal to t times y1 plus e minus t times x0, y0. And x0, y0 is given by the system, the same as we found before, which is 0 times x1 plus y1 equals 1. And 0 times x1 plus 0 times, I'm sorry, not x1, x0, y0 equal 0, which gives us that y0 is equal to 1, and we can take for x0, because we have any value for x0. We are not looking for all the x0, y0s, so we'll take x0 and x0 equal 0. I just need one solution. So y2 is equal to t e minus t 1, 0 plus e minus t 0, 1. So that's y2. So now the general solution of the system is y equal c1 y1 plus c2 y2 and now we go to the specific solution to our IBP. So we go for y of 0, and this will give us c1 1 of 0 because exponential of 0 is 1. 0 times e minus 0 is 0, and then we have only c2 times 0, 1, and this should be equal to the initial condition, which is 1 minus 2. Okay, putting the stuff together, we get c1 c2 equal 1 minus 2, which implies c1 equal 1, c2 equal minus 2, and therefore the solution is e minus t 1, 0 minus 2 t e minus t 1, 0 minus 2 e minus t times 0, 1. So if I put a little bit of algebra together, I can put this vector with this to get e minus t 1 minus 2 minus 2t e minus t 1,